Hello everyone and welcome back. We are now at part 2 of your demonstration video for Module 5, which is regression assumptions. You'll notice maybe I'm in a different location, so I'm just going to finish this video up. So part 1, if you just watched that, you already know, we walked through some of the more common and important assumptions of regression models, but also statistical models more generally. And we talked about the assumptions of normality of residuals, heteroskedasticity, or actually homoskedasticity. Heteroskedasticity is the violation of that assumption, and then linearity. And we talked about graphical ways to assess those assumptions and also statistical ones. So now we're going to wrap up by talking about regression outliers. We're going to talk about how to handle regression outliers with a technique called sensitivity analysis. And we're also going to talk about bootstrapping, which is a relatively straightforward solution for dealing with a lot of these potential assumption violations. I said this before, but I'll say it again. We are going to be moving pretty quickly through a lot of concepts for things like Cook's distance, bootstrapping, sensitivity analysis, and these are all concepts that we've covered in the lecture. So I highly recommend checking out the lecture for a little more clarity as to what these things are, what they represent, and why we use them. So I am down to line 94 of the week Module 5 handout, if you want to follow along with me. And so now we're going to talk about Cook's distance. So Cook's distance is a really nice measure of regression outliers. And again, in the lecture I talk about this in more depth, but there are certain cases when you run data analysis that may have sort of undue influence on your results. And if you think about the example we talked about with Andy Field, where we looked at album sales and advertising budget, right? If we included a data point that was very different from all the others on both measures, that could essentially pull our regression line in a very different direction. And so we want to be aware of whether or not there are such types of potential outliers in our data. The nice part is when we generate our diagnostics data frame, which is this data frame that you get by running the augment function in R, one of the actual variables that's calculated for you automatically is Cook's distance. And it's this variable right here called .cooksd. So that is extremely handy. We actually have a variable called Cook's distance that's calculated for us. The lecture shows how it's calculated and sort of conceptually what it represents. So this code on line 95 then just creates a plot in ggplot where we are producing a line plot of all of our observations and their Cook's distance values, and we're labeling each point with its ID so we can figure out who's who, and we're just putting the fitted values on the x-axis, the predicted values. That's not essential, we just basically need another variable on the x-axis, but it can sort of show us if there are systematic differences, if outliers are more likely to pop up in different places according to the predicted value. And then we give a title using the labs function, and then we add some lines to help interpret this. So this line, so there are two rules of thumb for interpreting Cook's distance. One is any Cook's distance larger than 1 suggests that observation should be excluded. And that we can see visually just by looking for 1 and seeing if there are any observations. And the other is 4 over n, where n is your sample size. So that's what we're putting in here. We're putting in a line going across horizontally at 4 over 250, which is our sample size. And we're making it a dotted red line so we can spot it pretty easily. So we'll allow this to run, and then we get our Cook's distance plot. And this actually looks very normal. You probably see a bunch of kind of clumped data points down here. That's absolutely great. That's actually what you want. You don't want a lot of individual points that have sort of more influence than others. You want your model to be reasonably good for all observations. So just looking at this plot, first of all, my y-axis starts at 0. That's the lowest possible value of Cook's distance. And it stops at about 0.175 maybe, or 0.2. So there are no data points in this data set with a Cook's distance greater than 1. That's excellent. So there are no observations that I would want to get rid of sort of automatically. There are, however, so first of all, 232 appears to be pretty far above everybody else. So that observation seems to be quite a bit different in terms of its influence on the model. And we do have some, here's our dotted line, this is our 4 over n line. We do have a handful of observations down here which we might consider maybe removing. So as we look at this Cook's distance plot, we do see maybe we could test whether or not removing these data points makes a difference. So what do you do with that, right? We can look at this plot and sort of say, okay, there are a couple, like what do we do? The solution is that you perform what's called a sensitivity analysis. And the sensitivity analysis goes like this. You take your original model with all observations, and you compare the results of the original model with a model where only the largest Cook's distance values are removed. And you compare that model, those two models, with a third model where you remove all but all the 4 over n observations. Okay? So I recommend doing three different variations. Original model, highest Cook's values, and then all of the potential Cook's values that are too high. And then you just look at the results, and particularly you pay attention to the standard errors and also the size of the coefficients. And hopefully they're not that different, and hopefully the significance and the direction of the coefficients don't change. And if that's the case, you can actually kind of wash your hands of it, which is kind of the best case scenario with the assumptions. You want to be able to prove that they're not having a huge influence on your results and that you can generalize your results to your larger sample. So let's proceed with a little bit with this approach. So this is our original model. I'm just pulling it up again. So this is a summary of that original model. So going back all the way to the first part of this video, we had an outcome y, and we had 3 predictors, x1, x2, and x3, and then our data were skew 1. And our only significant predictor here was x1, and x1 was significant and positively related to y. Okay, so now let's run the same thing, just removing the largest Cook's distance. And here, the largest Cook's distances are generally, let's say, around 0.1 or higher. So that'll take out about 3, maybe 4 observations. So to do that, I just create a new data set where I've removed those observations that have Cook's values that are larger than 0.1. And this is the code, so I'm going to create a new data set called trimmed, and it's going to start with the diagnostic data set, and then I'm going to filter all those observations with Cook's D's less than 0.1. So you filter in, right? So when you filter, whatever you filter to, it keeps those observations in the sample. So everyone with a Cook's distance below 0.1 will stay in. Everyone who doesn't meet that criteria will be kicked out. So let me just run this line here. And here's my new data set trimmed. And sure enough, I now have 247 observations instead of 250. So these 3 people, and I've added the IDs here, right? So I actually can look these people up in my data frame. So person 232, 61, and 206 were all removed in this first trim data set. And then I just run the model again, and I just call this data equals trimmed. So this model is high Cook's removed. So we run that. We look at our results. You know, offhand it looks pretty similar, right? X1 by itself is still significant, highly significant and positively related to y. The others are not significant. Okay, so then I'm going to do this one more time. So now I'm going to remove all values that are greater than 4 over n. And 4 over n in this case is 4 divided by 250. I can do that math in my head, or I can just do it in a calculator real quick. So it's 0.016. So that's going to be my new cutoff. So I'm going to produce a new data set, call this trimmed again, PROD trimmed, and then start with diagnostics, filter, Cook's D less than 0.016. So run that. And this one is down to 232 observations. So I've essentially removed 18 observations, and those are all the observations that I see here, including this big one, which are above the dotted red line. So all those are removed, and so this, then we just rerun this model, and we switch in our new data set. And then we get a summary. So again, we look at the summary, and okay, maybe a little bit different, right? This coefficient got a little bit bigger. It was 0.7 and now it's 0.8. Otherwise, the other two coefficients are not dramatically changed, and they're still highly non-significant. Okay? And notice our R-squared changes a little bit, right? Our R-squared's 0.11 here. It was 0.08 with the smaller number removed, and it was 0.07 with all the observations left in. And that actually makes sense, because what we're removing are observations that don't fit our model, right? And so if we remove a lot of observations that don't fit our model, we actually will expect the R-squared to go up slightly, and that's totally normal. Okay, so now we can put together a little comparison table, and this is great for a paper. This is actually its own section in the results. You can call this a sensitivity analysis. You can describe exactly what we've done, right? We've generated a Cook's distance for each observation. We've filtered according to these two criteria. We reran the model 2 more times, and we're comparing the results. And then we're putting the results in a summary table. So the package here is model summary. We've used this before. And then we create a list. So we're going to call this list models, and it's going to be the 3 models that we've run. So linear model 1, that's my main model. High Cook's removed, that's just a handful of observations removed. And then this is the model with everybody removed. And then we can get a model summary. Let's see, models. Yeah, there we go. And then we get a model summary in markdown format. And I apologize, this is probably, the type on this is probably not super big, but you can see this in your handout. So here's model 1, this is my original model. Here's model 2 and model 3, and we can track our observations, right? It keeps track of our observations, so we go from 250 to 247 to 232. Our R-squared goes up slightly. Our AIC and BIC, we'll talk about what those are later, go down, which is a good thing. And our model gets more predictive. But what we really want to pay attention to is the coefficients of interest. So x1 was significant in the original model, and the standard error here is 0.16. And in model 2, it's again significant, about the same size, very small difference. The standard error is 0.15, and here it goes up slightly to 0.85, but the standard error again is right around 0.15. So as I'm looking at this, I see very few differences between my main model and my model with a few people removed, and my model with everyone removed according to the 4/n criteria. So if I put that in there, what I'm arguing is, in my sensitivity analysis, is that my results are not sensitive to regression outliers. So in other words, regression outliers are not an issue. Even if you remove those observations that might be regression outliers, the story, if you will, of your model does not change. So that's called a sensitivity analysis. And it is really, really handy. It's also very useful in any situation where somebody says, did you try this? Because you can say, yes, I did, and it didn't make a difference. So essentially you're having kind of a debate, a back and forth with that hypothetical reviewer or committee member or someone else who is asking about other things that you could have done. All right, just a couple other things to show you. So first of all, I want to show you how to check for multicollinearity. We talked about this at length, well maybe not at length, but at least a little bit in the lecture. Multicollinearity is this concept that your predictors should not be too strongly related to each other and the outcome. If they are, then it's very difficult to get stable and unbiased estimates for those predictors. And so you check this by using a statistic called the variance inflation factor. And this is very easy to do with a regression model. The package you need, though, is called CAR. So if you don't have CAR, you want to come over here to Packages, click Install. Now I already have it, and just type in CAR. This is short for Companion to Applied Regression. Companion to Applied Regression. It is a really handy package, and it has this built-in function called VIF, and you just put the name of the model and it'll estimate it for you. And so here we go. You get a VIF for each predictor in your model. The VIF for x1 is 1. The VIF for x2 is 5.3. And the VIF for x3 is also 5.3. The rule of thumb is, at 5, you start to be concerned. At 10, one of those variables should really come out. So I might be inclined to leave these in. I might also want to try dropping x2 or x3 to see if that changes their significance. If these were higher, like if x2 was 10 and x3 was 11, I definitely would want to eliminate one of these. And this happens a lot. What I say is that in models, variables typically go bad in pairs, right? So you might, let's say you introduce two variables, related to something like SES, right, that measure SES in a slightly different way. It could be that those variables are going to be too similar to each other and you can't leave them both in the model. So you kind of have to make choices about which to include and which to exclude. So that is multicollinearity. Pretty easy to do using the CAR package. And now finally, I want to show you how to do some bootstrapping. Again, the lecture has a nice discussion of what bootstrapping is. In short, bootstrapping is a resampling technique, an intensive resampling technique, where you go back to your observed data, your sample, and you create artificial samples that are the same size, where you are sampling from your original sample with replacement. And so here we're actually going to create 1,000 copies of our original data set, except they're going to be resampled. So they're going to be slightly different because the same person can be represented multiple times in the data using bootstrapping. And then we're going to run that model 1,000 times, and we're going to average the results. And the reason we do this, the main reason you bootstrap, is for in order to obtain accurate standard errors. So the standard error, the thing up here in the linear model, thing in parentheses, right? That's a standard error. This is being somewhat difficult. Get this back up. And here, this is the standard error in the regression. Why do we care so much about standard errors? Well, the estimate divided by the standard error gives us our test statistic, right? Our t statistic. And that corresponds directly with a p-value. So the standard error is really important because it kind of sets the starting point for what your test statistic and p-value might be. So there's a really nice package from Roger Peng at Johns Hopkins that I like quite a bit called Simple Boot. And this just implements a really simple bootstrap for regression models. So again, if you don't have Simple Boot, you want to install it. And you get this little message, Simple Bootstrap Routines. And then we're going to create a new object called Bootstrap, and that is going to be a bootstrap using this lm.boot function of linear model 1. And the only option you need to specify is how many replications. That's what R stands for. R stands for replications. So here, R equals 1,000, which means we're replicating our sample 1,000 times. Hard to believe, right? It's creating 1,000 copies of your data sampled with replacement. It's running that model 1,000 times, and it's averaging the results, which is pretty amazing. And then we get a summary here. And look how fast. Done. 3 seconds, right? Isn't that incredible? I get amazed sometimes with how fast we're able to calculate this stuff. So 1,000 times it ran that model, and then here's the summary. And what we really want to pay attention to are the down here where it says bootstrap standard deviations. Now these are a little bit different from standard errors, but they're still useful. So these are the things we want to pay attention to. I think it's even better though to actually go a step further and create confidence intervals. So that's what this next thing does. This is another function from the Simple Boot package. It's called perk-lm, and this creates percentiles and confidence intervals. So what I'm going to ask for is a confidence interval, a 95% confidence interval for each of the estimates in my model. And so here's my intercept. And my intercept, by the way, was not significant in this model. So what we want to look at is, do the bottom, the 2.5% and the 97.5%, both contain 0 in the middle. In this case we do. And so we go from negative to positive. That means this estimate is not significant. X2, same thing. We go from negative to positive, not significant. X3 is not significant. X1, however, is. And the 50th percentile, or the median value, is going to be really close to my actual estimate. So it's 0.74. So this confirms, using bootstrapping, my story, which is that X1 is significantly related to my outcome. All right. Well, folks, we made it. We've made it through both of these sections. Just to recap, we started by talking about regression outliers, and we used ggplot to create a plot of Cook's distance for each observation. And then from there we performed a sensitivity analysis where we compared 3 models: our original model, our model with the largest Cook's values removed, and our model with all 4/n values removed. And then we just looked at the results to make sure they weren't that different and that our story did not change, and it didn't. And then finally we used bootstrapping to get more accurate standard errors for our estimates, and then we created a confidence interval. And based on this, it looks like even with the possible issue of assumptions, that our estimate looks pretty robust. Although, again, we want to keep in mind, in this case we saw an issue with linearity, and bootstrapping will not necessarily fix linearity. So we might want to go back with this model and see if there's a squared term or something else we want to introduce as well. All right, so that's all I've got. I hope that helps, and we'll see you next time.